The idea here is this. Let f of x be defined for all x in some open interval containing c, except that f need not be defined and often is not defined for the functions that we typically consider at c itself. If we're going to be able to write the limit of f of x as x approaches c actually equals infinity, then, well, what might the picture look like? Somehow the graph is becoming arbitrarily high. The function value is arbitrarily large, becoming arbitrarily large in this interval, and it's going up, up, up on both sides. So something maybe like this, and then something maybe like this is the typical picture that we think about if f of x approaches infinity as x approaches c. So what does this mean? Giving any positive number m, well, let's see, positive number m, let's go with m right there. So horizontal line, or an attempt at a horizontal line. There we go. For any horizontal line m, no matter how high we might draw it, there exists a delta. Let's see, you don't want to go too far to the left or too far to the right. This is going to be, that's too far to the right. Let's bring it in a little bit. And since I had to bring that one in, I want it to be balanced on each side of it. That's exactly the same distance on both sides. So, well, close. C plus delta, C minus delta. And look at the vertical lines associated with this. Maybe. I had to fudge it just a little bit. There exists a delta greater than 0 such that f of x is greater than m for any x in that interval except possibly at c where it's undefined. So I just want to make sure that as long as I'm close enough to c, that if I evaluate the function anywhere in there, it's going to hit above that horizontal line. If I move the horizontal line up higher, then I might have to shrink the interval around c, get closer and closer to c, so that it's going to be higher still. So as a rule, the higher the m goes, the smaller delta has to be in order to make this happen. Now, we can do a similar definition, turn the graph upside down, and talk about what it means for the limit of f of x as x approaches c to equal negative infinity. Becoming arbitrarily large in the negative direction, unbounded below basically, and we could write a similar definition there. Now, try to be as clear as possible. To say that the limit equals infinity is not to say that the limit exists. Our definition of what it means for a limit to exist, it has to equal a real number. It has to equal L, where L is positive or negative or 0, but not go off to infinity. Writing infinity is just being a little bit more specific than DNE. Technically, this limit does not exist. We write infinity to describe the manner in which it fails to exist. So it's a little more specific than DNE. If I give you this limit on the test and you say DNE, while true, is not the answer I'm looking for. If you can be as specific as positive infinity or negative infinity, you want to go ahead and do so. Now, what we'll see is that for those vertical asymptotes where the graph goes up to positive infinity from one direction and down to negative infinity from the other direction, and the two one-sided limits don't, well, what I just said, don't go to the same infinity, then really all we can say is DNE. If we're talking about the two if we're talking about the two-sided limit. Sometimes we'll break it down and talk about the two one-sided limits. In that case, all we can say is all we can say, but here we can actually say positive infinity. Example 1, let's be as specific as possible here. We are talking about the one-sided limit here for the first couple of them. X approaches 3 just from the right. We could draw the graph, and I think it would become clear, but hopefully it's clear enough without the graph. If we were to use a table of values and choose x equal to 3.1, 3.01, 3.001, all values slightly greater than 3, what would we observe about the y values? They get big. 3.1, 3.01, 3.001. We're looking at, I want to say 10 for this one. 3.1 minus 3 is 0.1. And 1 divided by 0.1 is 10. For this one, I want to say 100. 3.01 minus 3 is 0.01. And 1 divided by 0.01 is 100. And for this one, I want to say 1,000. 3.001 minus 3 is 0.001. 1 divided by that is 1,000. So we get closer to 3, the numbers grow larger. 10, 100, 1,000. And we don't have to consider what's going on the other side of 3, at least not until we get to the b part. So this equals positive infinity. It's just the one-sided limit. The other side is doing something else. If we say x and 1 over x minus 3, 2.9, 2.99, 2.999, approaching 3 from the left. Is this negative 10? Mm-hmm. And negative 100? And negative 1,000? Get a number that's just a little less than 3. Subtract 3, you get a number that's a little less than 0. If you take 1 and divide it by a number that's a little less than 0, you get a great big negative number. So this one equals negative infinity. Of course, neither limit exists, but we can be as specific as positive infinity or negative infinity in the manner in which they fail to exist. However, for the two-sided limit, we've basically explored all that needs to be explored about this. Since the two infinities don't agree with each other, it's going, what, from the right is going up, from the left is going down. I like to say plus or minus infinity, but really that's not appropriate. So the best we can do is say DNE. And that's a little unsatisfying, but that's what we say. What if we square the x minus 3?
It all goes to positive infinity?
It will go to positive infinity because that'll cause it to go up both ways in a little bit more extreme or less extreme fashion. More extreme. If x equals 0.1, that's going to be 100. X equals 3.1. Then it's going to be 100. If x equals 3.01, I guess it'll be 10,000 in that case. So yes, it'll increase in a more extreme manner. Example 2. In the past, when this section has gotten included on the first test, the main limits test, I'll usually put a problem like this on there, where I think the first one, you just plug in the 3. The second one, you factor the numerator and denominator and divide out the x minus 1. And the third one, you do that, and the limit still doesn't exist, but you have to talk about the limit at infinity. So I don't even know if I want to do the first one, what it would be something like this. Whatever that works out to be. This one, since we've kind of been there and done that, Check my arithmetic. Did I do that right? The last one, though, we can do the same sort of thing. Because it's the same expression that we're dealing with. It's going to be 2 over x minus 4. But the limit as x approaches 4, if x is a little more than 4, we get positive values. So what we can say is the limit as x approaches 4 from the right equals positive infinity. But the limit as x approaches 4 from the left equals negative infinity. So the two-sided limit, the best we can say is that it simply does not exist. It's going to positive infinity from one direction, negative infinity from the other direction. So this limit, and maybe put it up there somewhere, does not exist. What did the first one work out to be? Did you want to get that?
-2.
What, negative 2? Negative 2? All right, thank you.